Should be going. There we go. So just a little bit about me. For those of you who haven't met me, I think I've only had one of you as a student before. But yeah, I'm a 6-year PhD student in the WIN group. I'm hoping to graduate here early summer or sometime in the summer. My research has been focused on the stuff that the WIN group does, which is organic semiconductor devices, specifically solar cells and photodetectors. Happy to talk about that if you guys want to learn more about it or just discuss it. And I have a pretty heavy interest in data science and programming and analysis and stuff like that, which is why I asked the question about Python. And I'll talk a little bit more about that at the end as well. Okay, so here's kind of our overview for the lab, the entire lab. So today we're just going to go through some of the methodology background, so talking about the instrumentation and a little bit of the theory behind how they work. We'll go through the data collection process and like making the standards and all that stuff. We'll do some data processing using Excel. And then we'll start a little bit of the analysis looking at the actual end data that we want to be getting from this lab. So my plan for Friday is that you guys will go home after this one and work to, do some of this processing that we talk about today. Write down any questions that you guys have or problems that you're into, and then on Friday we can go into depth on those to try to solve them together. And then we'll probably split into lab groups, I guess, to work on that analysis and get those plots generated and things like that. And then next Wednesday, I think this will be an optional lecture because some of you did indicate that you wanted to learn how to use Python for some of this stuff. And I think it's a really useful skill to be learning and practicing. So on Wednesday, I think we'll try to do some of the analysis that we're doing in Excel. We're going to try to translate that into Python code to make it more extensible and portable so that you could see how you could use this if you're doing this for a job, for instance. Okay.
So you have Friday on there. Are we not meeting on Monday?
I don't think we are. So the schedule that's on the syllabus says Wednesday, Friday, and then next Wednesday. I'll have to double check that. But we could feasibly change that to Monday if that works better for everybody else.
Yeah, I was under the impression that the class was Monday, Wednesday. I didn't know we had class on Fridays.
Okay, maybe you're right. Maybe it's Wednesday and then the next one is Monday and then Wednesday after that. That might be right. I think I might have messed that up. Is that okay with everybody if we do today and then next Monday and then also Wednesday? So
yeah. So
okay.
Then the lab report would be due in 2 weeks. Is that what you're saying?
Maybe. Like I said, I'll adjust that as needed because it's a pretty in-depth lab report that I'm having you guys do, and I don't want to make it. I don't want you guys to run into a time crunch with it or anything like that. So we'll talk about the due date.
Okay. Thank you.
Mm-hmm. So yeah, moving on to kind of the actual content of the lab. So this is the instrument that we're working with for the data today. It's unfortunate that we don't get to actually run the experiment ourselves because it's a nice hands-on experience. Not that anybody is going to be going into GCMS analysis for their jobs or anything, but the process of experiment design and like running these things and getting the data and processing it is a very useful and translatable skill. But anyways, this is the instrument. So it kind of the experiment actually kind of runs right to left. So the GC, the gas chromatograph, is there on the right. It's got this dB5ms column, which you guys can look up to figure out the details of that, like what the solid state or the solid phase is in there. And this is inside this oven. That's the main component here of the GC. And this oven basically runs through a temperature cycle that elutes all the stuff that you injected at different times and then passes it in over here to this mass spectrum detector, which is equipped with this electron ionization source, a quadrupole mass analyzer, and it can tackle a range from 40 to 550. This is mass to charge ratios. And the typical scan rate is 2.4 hertz. So every 2.4 seconds, it takes a reading, basically. Okay, so like I just kind of went through, this is a more cartoonized approach to this. So now it's left to right. So you inject your sample, it elutes through this column here, and the process of eluting through here separates the chemicals that are in your mixture because they have different interactions with the column itself. And then at the end, they're passed into this mass spectrum thing where they're ionized first. This is the EI, Electronization Source. This is focused using some electromagnetic fields passed into this quadrupole, which is just a schematic here. So it's a magnet with 4 different poles. And then by alternating the frequency of this quadrupole, you're able to separate the ions by mass. And then you pass them over to this electron multiplier, which then reads a current, basically. So that's how this whole thing works. It's pretty simple in principle, but the actual process and analysis and experiment design that goes into this can be really complicated. So I encourage you to go through the textbook and read about this and all the different nuances that are in there. So here's just an overview of kind of what I've already said, which is this gas chromatography process. I don't want to go through and read all these things in detail, but this is kind of more for your reference as you're writing up the reports. One of the main things to note is that the injection port is heated to a pretty high temperature because you want to really quickly vaporize the sample. So you want to get rid of all of the solution that it's in. You want to just keep the components that you're interested in. And then the column is cooler after the injection port, and this causes the analytes that are in there to condense within that column. And it says in the first few meters here, and those columns are actually really, really long. They're coiled up inside of there, and they're like 30 meters or something like that. So sorry, I don't know if you guys can hear my dog screaming at a siren in the background. And then, yeah, so the way that the chemicals are eluted is by using a temperature program that you basically have to calibrate for each mixture that you want to analyze. So you ramp the temperature at different times to different temperatures, and you hold it and all this stuff. And what that's trying to do is to make a nice clean gas chromatograph at the end so that all of your components are separate from each other so you can easily analyze them at the end. Then once they're at the end, they get passed into the MS system, which they're ionized first. So this is done by producing these high energy electrons that are from a heated tungsten filament. And then those electrons are shot towards the molecules basically, and they interact with them to ionize them. So this is a hard ionization technique, meaning that the energy is enough to break up the molecules sometimes, depending on the bonds that are in there. And so once those ions are formed, they get focused into that quadrupole. And the quadrupole filters the ions using this oscillating magnetic field. And then if you scan the frequency range of that, basically you only allow certain molecules with a mass to charge ratio through, which you know. And then that goes to the detector, which reads a current. And then you're able to generate this mass spectrum for your sample, which is a really cool technique. And yeah, so this is the physics of how it makes that electrical signal. But anyways. So I already run through this. This is EI. It's an important thing to note because it's going to determine the nature of the ions that we're looking at here. So the main thing to look at is this general formula. So you have a molecule that elutes. An electron is interacting with it in some sense. It doesn't necessarily mean that it hits it directly because, I mean, most of space is just empty space, but they're close enough to each other that it transfers some of its energy and allows this reaction to occur where you generate a cation radical and then 2 electrons. And so this cation is what's actually detected by the mass detector. Okay, so I think probably Gwen went over a lot of that stuff in her lecture, or at least I hope she did. So now we can kind of dive into the actual specifics of this lab. Real quick, hopefully you guys were all able to download that zip file from GastroSpace, right? That has the data and all that stuff in it?
No.
Yeah.
No, Lily? It should be posted on GastroSpace. It's a zip file, it's just data.zip, and it has some raw data, some process data, and some other things in there for your reference. So for this lab, our premise here, it's kind of like we're working for, I don't know, the EPA or something like that. We want to analyze 3 different gasoline samples to detect certain components of them and quantify them, because when you're selling gasoline anywhere in the world, it needs to meet some certain criteria in terms of the concentration of different components of it. And so we've picked 3 of them for the gas just to try to get a sense of how this would work. You can do it for anything that's in that gasoline, and they do typically do it for lots of different components. But we're specifically going to be looking at benzene, toluene, and this MTBE compound, methyl tert butyl ether. This is an additive that's added to gasoline. I'll talk about that in a second. So we might not see it in our samples, but we want to make sure, if it is there, we want to see it. So that's why we're analyzing it. And so the procedure that we're going to be using, the way that we're designing this experiment, it's kind of following this guidelines from the FDA for producing accurate and valid chemical methods. I included a PDF in that folder so you guys can peruse that. It's a really long document, but it goes over the reason why we're doing this experiment the way we're doing it. And yeah, so here's our components, our target analytes that we're trying to get. These are their average atomic masses here. And our goal at the end is to report the concentrations, so molarity, of each of these different components in the 3 different gasoline samples, including some confidence intervals, hopefully. So in order to do this, we actually have to do a lot of extra work to get to this point, and we need to make some calibration curves. So this is the background of MTBE, kind of just for your own reading. It's added to raise oxygen content. It makes it so that it combusts more completely in general. This is no longer really added. Most people use ethanol nowadays, but it still can be found in gasoline. And so we want to know if it's in any of these gasoline samples. So for our standard solutions, we need to construct a calibration curve, right? You guys are all familiar with the concept of this, hopefully from Gen Chem and stuff like that, right? Where for some unknown sample, we need to calibrate our instrument so that we know specific concentrations of these things and what kind of signal we get out of our detector for these different concentrations. So we're preparing these stock solutions with known amounts of our 3 different analytes. And we're also doping it with this deuterated toluene. This is going to be our internal standard, which we're going to keep the concentration of this consistent for all of our different samples, including the gasoline. And this is how we're going to reference our retention times from our gas chromatography, as well as the peak areas for the mass spectrum part of this. So this is the table from the manual. It just talks, it's the volumes of each of these things in microliters, as well as this 1-chlorohexadecane, which is just our carrier solvent. In this case, this gets vaporized at the injection port, and it's not super important. It's basically just a way to dilute all of these things to proper concentrations. So here's the procedure for preparing these standard solutions. So each one of those stock solutions that we just talked about, you take 20 microliters of those, you dilute it again with another 1 mil of the 1-chlorohexadecane, and then 50 microliters of the internal standard stock solution. And the details of this standard solution are also in that manual file. And then we do this 3 times for each standard solution. So we make 3 different dilutions of each of those stocks. And then each of those is separately run 3 times. And this gives you triplicate results. This is part of that FDA method validation thing. So we get 27 different GCMS runs that will allow us to construct these robust calibration curves. And so these data are basically summarized for you in these 2 files here. These are in the reports or integration reports folder in the data file. And so we'll be using those in Excel to do some of this analysis. But before we get to that, we'll talk about how this data would actually be extracted from the real data. So here's some predicted mass spectra that we would expect to find from each of these components. And we're going to use these to kind of compare our actual data to figure out if we're actually seeing what we think we're seeing. So one thing I want to draw your attention to is that this MTBE one here is a little bit different than we'd expect just based on its chemical structure. So all of these ones, the dominant mass peak is at their average molecular weight, basically. So benzene is at like 78, toluene is at 92, and then deuterated toluene is at like 98 or 100. So all of these things basically agree with these structures, but this MTBE one is slightly different. So the main peak there is at 73. So can anybody think why this molecule doesn't occur at 88 as its main peak? Anyone have any ideas? Remember the ionization method that we're using here. Anyone? So how are we ionizing these molecules at the end of the GC column? What's the method? No one wants to speak up. It's EI, right? Which stands for what?
Electron ionization.
Electron ionization, right? And so what's special about that particular kind of ionization? Is it hard or soft?
I think it's soft.
It's hard.
Oh,
right?
okay.
So those electrons have enough energy, like I talked about, to potentially break some bonds depending on the nature of the chemicals that are being passed through the beam there. And so as an exercise for you guys, I want you to think about what could break here and what structure has a molecular mass of 73 with a charge of 1. So that's the main peak that we see for this, and we don't see a higher one, which you'd expect if it didn't fragment, but we don't see the 88, we see 73. So we're going to use this to kind of calibrate our instruments. And then, so once we've done all of those standards and we collect the data for them, we do the same with our gasolines, our unknown. So we take the 20 microliters of our raw gasoline, dilute it the exact same way, and then add the exact same amount of our internal standard, because like I said, we're going to be using this to calibrate the retention times as well as the peak areas. And so for this lab, I generated some random data. So we have 3 different gasoline samples. And instead of doing each one of these also triplicate, we just did it triplicate. So each sample is only run 3 times, not 3 different vials of dilutions. In theory, we should probably do also 3 different solution preps and 3 different runs for each of those, but this is enough data, I think, for us to make the point. And so these data are summarized in the integration reports gasoline.csv file. And so here is an overview of the general process that we're going to be using for the data analysis. So we create those calibration curves, which we'll need to spend some time normalizing those and making sure that they're accurate. We'll create some sample chromatogram and extracted ion plots so that you guys can use those in your actual reporting because they're useful for talking about this stuff. And then once we've had those things, we can normalize our gasoline data and extract the relevant ion signals for processing. And I'll show you kind of what this means because those samples will be much messier than our standards, obviously. And then from that, we can calculate our final concentrations of each of these analytes in the gasoline. And to do this, we need to make sure that we follow all of the dilution procedures that we did so that we can report the actual concentration in the raw gasoline as it is. So, okay, here is just kind of a screenshot of that OpenChrome software. And we're going to switch over to that in just a second to kind of go over it. So if you want, make sure you open up that program if you have it, and then you can kind of follow along. But basically what it shows you for any of those data files that are in the raw data folder, it shows you a chromatogram. And then from this, you're able to look at the extracted ion signals. So like the counts from each of these different peaks. So you can actually select any point along this curve here. Most of them are really low in their total number of counts. And so for our standards, which we prepared, right, we think there should be 4 different molecules in there. So this looks good from just a first approximation here. We've got 4 different signals, and hopefully each one of those corresponds to different ions that correspond again to our actual analytes. So for this one, I selected the scan that's just right at the peak of this signal here. And we can see that the dominant component there is this mass value of 73. So it's a pretty fair bet that this is the MTBE from our solution. So that's good. And then over here on the right, so the data that are shown in this graph here are also tabulated here. So for each of these different signals, it gives you some intensity and counts, as well as an intensity as a percentage of the maximum one. The counts are the main thing that we're interested in. And then when we're actually extracting the data to make like our calibration curves, what you do is you'll select the entirety of this peak. So you'll select all the scans that make up that peak with some baseline saying, below a certain threshold, we don't want anymore. And then you integrate that and count all of the charges that are in there to get the total peak area. And so we'll go over to OpenChrome and we'll do just kind of a simple explanation of how this works. The data for this has already been kind of extracted for you guys because I know that some people probably can't get this OpenChrome software to work, but I want to show you how to do it anyway so that you can play around with it. So let's go over to OpenChrome. So when you first open it, you guys can still see my screen, right?
Yeah.
Yeah, good. So when you first open it, you get all these green boxes here. The only one we really care about is this data analysis window here. So if you click on that, it'll open up that window. And then in order to load in the chromatograms, so let's see, I want to go to our data files. So this is the same data structure that you guys have. So the raw data are these .d files. If you open up one of those and you double click on the data.ms file, it'll load up that chromatogram. And so this is what we see. This is what we saw from the PowerPoint, right? And right now, the mass scan chart down here is just set to the first scan. So you can see this is scan 1, and it's got a low number of counts for this 44. We don't care about that. What we care about are all of these different peaks. So let's go through, and if you double click kind of above it and try to get it on the peak there. I haven't found a good way to actually like browse through the scans yet, but anyways, this works. So there's our dominant peak or our dominant mass or ion at that peak from this one, 73. Let's check on this one. Try to get the peak of it. So this one's 78. So I believe this one is benzene. And then let's check this one. This one's 98. So that one should be the D8 toluene, I believe. And then this one, which I didn't get the peak of it, but anyways, it's like 91, 92. So this is just the toluene. So this is a good indication that our standards are accurate, right? We know that we found 4 major components in there, and they agree with the mass spectra that we were predicting from those molecules. So the next thing to do would be to actually integrate each of these peaks because we need the area, right? So OpenChrome has a way to do this. If you right click on the chart, you can do, let's see, we want to do peak detector, and we'll just do the first derivative. There's a bunch of different ways to do this, but I found the first derivative one works the best. you can play around with the conditions here to try to like only find the peaks of interest. The system options will generally work pretty well. So let's do that and see what it gives us. So we can see here that it found some peaks that it thinks are in there just based on the derivative of this data. And some of those we don't want, right? We only want these 1, 2, 3, and 4 peaks. But to actually look at those, we actually need to go up here, I believe, and we want to show scan list. And there we go. So these data here, these correspond to each of these peaks that the integrator found, or the derivative found. So if you click on them, you can go through and you can see, so down here, this is now the integrated signal of that whole peak. So this is how those areas are extracted that are in your integration reports files. I'm obviously not going to make you do that. Well, okay, we haven't got there yet. These are the retention times. So just from the peaks, we find the retention time, and it's taken just at wherever the peak occurs. To calculate the area now, there's another function. So we want to do, where is it? Peak integrator down here. And we can just use the peak integrator trapezoid function. And again, use system options. And this will fill out this area column right here. So now these areas can be used to correspond and build our final calibration curves. If you wanted to clean this up, you can go through and you can like, let's see, you can just delete individual scans here. So like delete peak, just delete that first one, sure. And then it looks like the third one there, also delete. Not going to go through and do all these, but anyways, you could clean it up to only get the data that you're interested in. So yeah, the general procedure would be to open up each one of those different files and do this process of finding the peaks, calculating their areas, and then you'd take these data and you'd put them into that integration summary report file. So there's a couple other things that we might want to do. So you probably want to include some of these chromatograms as well as the mass spectra in your actual reports. And it's not good practice to just take screenshots from your analysis software like this. You actually want to take the data and plot it yourself and make a good figure for it. So from OpenChrome, it's nice. You can actually just export the entire thing here. I want to make sure I export chart selection. We'll export a comma separated value file. And let's put it in the folder that we're actually in. So data for lecture. We can put in the raw data and we'll say this is C153 AC1, and then chromatogram.csv. And sure, we can just select all these things, keep them in there. That's okay. Data has been exported successfully. So let's open that up real quick. 1 second, let me get to that file. Just want to show you what it looks like. So labs. Second, I guess I can show you where I'm going here. GCMS, data for lecture, saved in the raw data. And then here's a CSV file. So if we open this, Excel will automatically open CSV files unless you've changed your configurations on your computer. And so that opened up this file, which is just the raw data. And it's, let's see, we have time in milliseconds, which is not super useful. So we could convert this into minutes if we wanted. But let's just plot it real quickly by itself. So I selected that, insert, and let's do, it's a scatter plot, but we want connected lines. And so we can see that that agrees with what we just got from the actual OpenChrome software. So now you're free to style this or layer different runs on top of each other to do some analysis and stuff like that. Of course, wanting to label all these things, which we'll go through in a little bit. But this is the general process. So if you wanted to extract the data to work with it on your own, you need to export a CSV and then go from there. So let's go back to OpenChrome real quick. Something else that you probably want to do is, yeah, these mass spectrum peaks here. So let's grab that first one. So like I said, so all the data is tabulated over here. You can also right click and export from here. So let's do the same thing. We'll do, instead of chromatogram, this will be peak 1 ms, something like that. Doesn't really matter. And we want, yeah, intensity counts versus ion. That's fine. And if we open that file up now, hopefully it does it correctly. Yep. So actually, it only looks like it did one of the scans. I'm not sure how to get it to report the integration, but it actually doesn't matter too much because really what we want is just these data here. But there's a problem in that you'll notice. So the scale of our x-axis here, so the mass to charge ratio is not uniform, right? So it has a bunch of different values, just basically like if it records a 0 or below some threshold, it won't report that data for you. So in order to generate a plot that actually looks like the one from here, we basically need to fill in the data between these and basically add those zeros back in. So there's a way to do this in Excel, and I guess we can just kind of go through it now as a exercise. So let's see, if we just plot these as is. So anyone have an idea what kind of plot would be a good one to use for these kind of data? If we go back to this. So we used a connected scatter plot for these data here, which makes sense because it's continuous. But what about this? Anyone have an idea?
Could you use a bar graph?
Yeah, we'll use something like a bar graph or a histogram. So we do this here, and Excel thinks it's smart, and it plotted two different series. So it's not actually doing it the way we want, right? Like we want this to be our x-axis label, and then this to be the y-axis count. But it's not set up to do that yet. So this is why Python is such a great tool, is because we can specify these things much easier. But we can do it in Excel. It's just going to require a little bit of work. So I'm going to do, let's see, I can zoom in here so we can get a little bit better details. I'm just going to delete this row because I don't want it. And I'm going to select all of these data, and I'm going to insert a table. So this is a special thing in Excel where it'll treat all these data as one kind of unit. So this is table 1, basically. And now we want to go through and we want to make a new x-axis that basically covers all of the range that we want here. So let me select these data, and I'm going to change their format to make them a number so we can actually see what the spacing basically should be. So it looks like we're increasing by units of 0.05, basically. Like that's kind of the resolution, right? It doesn't look like there's anything below that. So if we increase the data there, yeah, so it's you know, we have data that's at 0.05, we've got a 0.1 and a 0.15. So it looks like that's kind of the spacing that we want. So I'm going to do that. I'm going to start from 40 here. I'm also going to set this to a number format. I'm actually going to set this whole column to a number format so this works better. And then with Excel, we can go through and we can just generate that data. So plus 0.05. And then if we copy this down, it's going to copy that formula. Let's see where we get to there. So we're going to have to do this a lot, right? Like we want to go all the way up to, well, let's see. Let's go back to our thing on here and see where we want to go to. So it looks like we go up to, yeah, okay. So all the way up to 100, basically. So we actually do need to go through and do that. So I'm just going to copy this down, way down. See where we are now, only at 60. So this is pretty tedious, right? But it's useful. Almost there. Okay, that's plenty. So the next thing we want to do is we want to fill in this column here with the counts from this column here. And so the nice thing about Excel is it has some cool built-in functions that we can use. Let me open up my reference here real quick. Not that one. 1 second. Oh. Okay. So we want to use a formula here to extract these values, basically. So we want to do something called Vlookup. This is a function that will take the value that we want to look up in a different table. So we want to select this value. And then we want to select this entire table as the place where we want to look up the value from. So what it's going to do is it's going to look for this value in this column of the table. And then we'll tell it, if you find that value, put this value into the cell. So this is the column index number. So the column we want to insert is 2. And then the last thing here, we want to use the keyword false. So you can see that true is an approximate match. So it'll round it. It'll do some internal rounding, but we want to find an exact match. So we do false for that. So let's enter that. and then we'll copy that formula all the way down, and we can see that all we get right now is errors. And so this is a bit of a problem. So we want to add some extra functions to this to make sure that this works well. So first thing that we want to add is let's inspect this error real quick. So let's go show the calculation steps. So it looks like, so it takes 40 and it looks in that table and it doesn't find it, and then gives us just the NA there. So this 40 value is kind of a problem. We want to make sure that it's actually looking at the same resolution as these things because we specified an exact match. So let's first go in here. I'm going to, in front of this term here, I want to use the Excel function round. And then I want to round that to 2 decimal places. And that should make it so that it finds things a little bit better. So, okay, so just with that, you can see we found this first one, right? So it found 40.10, and then it extracted that intensity from there. So the next one we should find should be 41.15. So if we scroll down, we can also see that. Now, the next thing I want to do is I don't want to have all these errors in the cell. So there's another function, and I know this is kind of in the weeds for Excel, but this is how you do data analysis if you're doing this on a big scale. So another function called if error. So we'll do this. So if we find an error, we want to tell it to put something else in there. So we can put 0 is our value if there's an error, and that's fine. And then if there is an error, other way around. So if there's an error, if there's not an error, first put that value in. If there is an error, we'll put 0 in, like that. So you can see for that first one, it did it correctly. Then we double click that all the way down, and we can see that instead of those errors, we now just have our data. So perfect. So let's label these columns, MZ, counts, and then we should be able to select all that data. That hotkey, by the way, is Control Shift and then the down arrow, and that'll select all the way to the bottom where the data ends. I was trying to get screen keys turned on before this class, but I wasn't able to get my program to work for some reason. So now let's see if we can insert a formula that makes sense here, or a graph that makes sense. So if we do that, it looks like, okay, it's still doing that. So we don't want that. Let me think here. So we want, let's go back to insert. Let's try recommended charts and see if that gives us a better, that one looks like it. So, okay, no, that's a line. We don't want that either. One moment. Looking at the key that I made earlier. So it is a column graph, should be clustered column. Why is that not working? Let's just try that. Scroll back up. Insert a, should be clustered column. So, okay, oh, 1 second. Let's just insert, do that again, sorry. Select the, nope. Select the data. So series 2 is the actual one we want. So I'm just going to remove that first series. I'm going to edit this series, and I want to use, yeah, this as the values. Sorry, scroll all the way back up. So that's that. So why is it not doing the labels correctly? 1 second. So let's double click on this axis here and see if we can get it to read our correct things. Let's see. Vertical axis, automatically select data. That should work. So it's fine. Okay, I'll just show you my key for the other one real quick. So this is eventually what you can end up getting to work. And I'm not sure why the data decided that it didn't want to correctly do that. But anyways, so we can play around with this once we get through kind of a discussion, and we can work together to figure this out. But for your actual reports, it'll be nice to generate plots like this, where you have the mass to charge ratio on the bottom, and then the intensity on the left. And so that closely mirrors what we see in here, where instead of, just taking a screenshot of this, we're able to format it much more nicely to include in our report. So yeah, we'll play around with that a little bit more once we get towards the end of class, or we can do it again on Monday, something like that. But same procedure here. Okay, so let's jump back to the PowerPoint real quick and talk about, okay, so here's kind of an example of what I was talking about, where if you export those CSV data for the different standards and stuff like that, you're able to then work with those graphs. So you can plot things like this to show that our different standards do in fact decrease the peak area for those different peaks, which is nice. We expect that from our data. And our peak for the D8 toluene, which is this one here, hopefully you guys can all see that. So this is the one that we're going to be using to standardize or normalize the data. So since we know the exact amount of D8 toluene should be the same in all of these different samples, we can apply a correction factor to all of these peaks to make sure that basically the height of these peaks, or actually the area of these peaks, is all the same. And also the retention times. We want to make sure that those are also normalized to shift all these things. Because you can see, like if we look at these peaks here, especially, the retention, God, kids, shut up. You can see the retention times change a little bit. And this is because the way the detector works, right? Like you can see that this one would grow up to here if it had more counts, but the retention times are only calculated based on the highest peak value. And so we actually want to normalize all of those as well before we construct our calibration curves. So yeah, this is what we just did. Basically, this is how to use the OpenChrome software. If you're unable to get OpenChrome to work at all on your computer after trying with different installations and stuff, then I can probably send those CSV data as a zip file to everybody, and then you can do your own plotting from there. But anyways, so like I said, this data has the heavy lifting of extracting all those times and peak areas and stuff has kind of been done for you, just because we didn't have a good real data set for you guys to go through and play with that OpenChrome software, and everybody has trouble getting it to work on their system. So those values are reported for you guys in those CSV files. So moving on to the actual construction of these calibration curves now. So this is kind of the real meat of the lab, is making sure that our curves tell us exactly what we think they're telling us. So we need to, like I said, we need to normalize all these things. So the retention times and the peak areas, we want to end up with a plot of concentration and molarity versus peak area, so that we can run those gasoline samples and quantify exactly how much benzene, toluene, and MTBE are in there. So we just talked about this. So we notice that there's a little bit of drift or jitter in the data for the retention times and the areas. And so we need to account for this. So we're going to go back into Excel and open up one of these, the integration summary and the integration reports files, and we'll do some analysis in there. So let's do that real quick. I think I have them open. Yeah. So this is the integration reports standard CSV file. So this is really similar to what you would get from an actual like GCMS run. You'd get a file that's like this with the sample name, the extracted ion mass with some tolerance on it, retention time, and then peak area. And so these data, you'd have to take these and basically normalize the areas to the D8 toluene peak, which we've said is 100, right? And then the retention times also. So it can be a little bit tedious because this data is not in a good format to make use of Excel's functions. And so that's what the integration summary is. It's basically all of those data taken and then just pivoted so that they're in a way that we can apply functions to them much easier. Before I go on, is everybody following this? Am I going too fast with Excel, or is this making sense how we're doing this? Because you guys are going to have to do this on your own. We all good?
Yeah, it's making sense.
Cool. So yeah, so these here, you can see. So let's look at this one, for instance. So sample 1, vial 1, run 1. If we go back to our report standards here, that's just these data here. So we've taken, this is our column header, this is the retention time, and then the area is the next column over. So back to the summary. So that's just these data. And we do that for each of the peaks that are in our standards. So how can we go about normalizing these data? Does anybody feel brave and want to venture an explanation as to what normalizing is? Why do we do it? I guess
it's basically to just make all the numbers like rise and fall with the same slope.
Yeah, basically. So like I said, we want to make sure that because there's differences in the injection volume, the time it takes to elute and stuff like that, we want to get rid of all of that noise in there and just extract the information that we want. And this is the reason we use this internal standard of D8 toluene. So it's only labeled as 100 here because that's the dominant mass peak, but this is the D8 toluene, right? This I think corresponds to benzene, toluene, and then the MTBE. So to go about normalizing this stuff, there's a couple different techniques that you could use, and you can do some research to choose kind of the best way to do it. I'm going to show you one good way to do it. So I'm going to convert all these to numbers so that Excel knows the proper format for them. So the first thing I'm going to do is I'm going to calculate the average of all of these retention times, because this is our D8 toluene. We know that this is our internal standard. So let's give an average for that, and we'll use that to correct all of the other retention times. So I'm going to average those values. And I'm going to do the same for the areas, because we know that all of these should correspond to the same concentration of D8 toluene, right? So even if our injections volumes change a little bit from run to run, because it's dependent on the total number of carbon atoms basically hitting the detector or ions hitting the detector, all of these numbers should be the same. So basically what we're doing with this normalization is we want to make all of these times the same and all of these areas the same. So in order to do that, I'm going to calculate some normalization factors here. So I'm going to do first RT norm factor and then area norm factor. And so for this one, I'm going to take that average value. So I'm going to hit equals in this cell. I'm going to grab that one, and then there's a hotkey in Excel. If you push F4, you can see it adds $signs to both the H and the 29. And that just tells Excel, lock this number in place so that all the calculations will only ever use that cell. And then I'm going to subtract the retention time for the given run. So if we do that, you can see that that one happened to be exactly the same as the average. So that's nice. But if we drag this down, we'll see that each one of these gets some small correction to that retention time. So we'll apply this factor in just a second. We're going to do a really similar thing for the area, but instead of a subtraction, we're going to do a division. So we're going to take this average area, again, lock that cell with the $signs, hitting F4, and then divide it by the area of the run. And so these now can be multiplied by all of these different areas, and it should make them all the same. So let's go through and we're going to apply these normalization factors to each of these data columns. So I'm going to do 73 RT norm. You can name these however you want, but this is just, I don't know, it's good practice. 73 area norm, 91 RT norm, 91 area norm. What's the next one? 78 RT norm, 78 area norm, 100 RT norm, and 100 area norm. So now we want to go through each of these columns and we want to correctly apply our normalization factor. So for this one, I'm going to say that this one is going to be equal to this retention time plus our normalization factor. And let's go and drag that down. So you can see that it changes the retention times, and there's still a little bit of jitter in this because this is not our standard, right? So this correction factor here was calculated based on our internal standard. So there's still a little bit of variation in our actual Analyte data, but you can see they're much closer to each other now. They're all between 1.31 and 1.32. So then same thing for the area. We're going to take the area from our run and then multiply it by our normalization factor and drag that down. And then a nice thing about Excel as well, so if we copy or select both of these columns and let's drag that same formula over to all of these, it should hopefully apply them in the correct way. And it doesn't look like it did. One second. So let's So what we're expecting, right? These should all be the same. It's because I forgot to lock the column values. So we want to take B2, we want to lock the column. So instead of hitting F4 to lock both the column and the cell, we want to just put a $sign in front of the K right there. So this tells Excel, stay with this column for that. Because we always want to use this same retention factor. And then same with this one, we want to put a $sign in front of that L. And now we'll double click that down. And now we should be able to drag this over, and that should, there we go. So like we were talking about, this is the goal of the normalization, right? All of our D8 toluene have the exact same retention time because we applied this correction factor to them, and all their areas are also the same. So I'm just going to quickly go through and make sure that these are all a number format, and that's fine. And you can also see that because Excel, isn't very smart, it added some extra resolution here to all of these extra decimal places, which come from multiplying by this factor. You don't want those really, so you can just kind of select these and then reduce the number of decimal places to round them to whole numbers. But then these now are our corrected areas and retention times. So that's great. So then the next step would be, since we have these normalized areas, we need to then know the actual concentrations of each of our analytes that are in this sample. So the first thing I want to do, Excel with CSV files doesn't save things like multiple sheets or formulas and stuff like that. So we're going to resave this as an Excel file in this same folder. We can name it the same thing. And we'll just save it now as an Excel workbook. And this allows us to save all that analysis and stuff for the future. So yeah, so let's go through the next step really quickly of calculating our actual concentrations of these, because the areas are great, but what we want to end up with is a concentration versus area plot, because that's going to be what we're going to use to calibrate for the actual gasoline samples. So I'm going to make a new sheet here, and let's go through together and let's kind of use Excel magic to calculate these concentrations that we need for us. Let me go back to PowerPoint real quick and see if I have, yeah. So we've got these times and peak areas normalized. We want to get the ion count versus the molarity, or the peak area versus molarity. So let's go, hopefully everybody has that manual opened up that has the details of the solution prep. And let's go through and figure out how we'd calculate the concentration from those data there. So I'm going to have you guys kind of help walk me through this. So what should we do? Let's make a table here in Excel that'll help us do this math. What data do we need to calculate concentration from those data that are in the samples or the standard preps? Anyone?
Would time be one of them?
We don't need the time, right? Because all that's been accounted for in this stuff here. We basically just want for each of these samples here, so standard one should have a certain concentration of the MTBE and the toluene and the benzene and the D8 toluene. So we need to know the molarities of each of these things for each of these different standards. And there's 3 different standards that we prepared, right? Different concentrations of those. So what are we given in the manual there? It's let's see, on page 4, step 2, prepare the Analyte standard solutions. So I'm gonna go through. I'm basically just gonna copy that table and the volumes and stuff. So we've got, let's see, maybe we want to do it some other way. Let me think here. Yeah, so we want to go the other way around. So we want to do sample 1, sample 2, sample 3. This is going to be MTBE. This is going to be toluene, benzene, and we also have our 1-chlorohexadecane, CHD we'll call it. We can calculate the D8 toluene later because that should be the same for all of them. So now I'm just going to go through and fill in the microliters that we add for each of these. 50, 20, 10. Toluene is 200, 100, 50, and then 50, 20, 10 again, and then 2200, 2360, and 2430. So these are all values in microliters, right? So if we want to figure out the molarities of each of these things that are in these solutions, how can we go about doing that? What should we do? What other data do we need? Thinking back to Gen Chem stuff. Anyone remember how to go from just a volume of something to a molarity?
Molar concentration.
Yeah, so we're gonna need some molecular weights, right? What else? What other properties of these chemicals do we need in order to figure out exactly how many molecules there are per liter of solution?
Density.
Need the density. Yep. So those things sound like really useful things to have for me. So why don't we make another table that has some of those values? So let's do MTBE. We'll do molecular weight, and we'll do density. We'll also do toluene and benzene. Do we need the data for the 1-chlorohexadecane in this case to calculate, like, do we need the molecular weight of it and the density? I think we can get away with not using the density of that, but we can discuss that later. But okay, so let's look these up, right? So a good resource for you guys is this NIST chemistry website, which will allow you to search for these chemicals. So I don't know, let's grab, let's see if it'll recognize MTBE, probably not. It did, great. So awesome, so it gives us a molecular weight. So let's just copy that, go back to our data table. That's our molecular weight. Let's see if it has a density for us. It might, we can see. If you can't find it here, Wikipedia is also great for a lot of these things. Wikipedia. Go to Wikipedia and let's type MTBE. It might also recognize that. Yep, it did. So a lot of chemicals are here on Wikipedia, and it has most of the information that you need. So there's again that molar mass, and it also has a density here in units of grams per cubic centimeter. So we want to make sure that we remember what those units are, because we might have to modify them for our calculation. Good job. Come on, what are you doing? Oh, I copied the link, that's funny. All right, we'll just type it in 0.7, oh my God, 0.7404. It's opening links for me, that's awesome. Remove hyperlink, there we go. Okay, great. So there's some of those. So let's get, can one person look up toluene, one person look up benzene, and tell me the numbers for those as well.
Molar mass for benzene is 78.11.
78.11. Got a density by any chance?
Hold on.
No worries. So all of these things, right? You can do this by hand with a calculator like you're used to from Gen Chem and OChem and stuff like that, just going through each one and calculating them. But with this class, I want to emphasize how to do data analysis on a larger scale and what you'd be doing in grad school or a job or anything like that. Like you wouldn't be expected to go, like imagine if you had to do this experiment for, 100 gasoline samples in a day or something like that. You wouldn't want to be doing this by hand for everything. So you want to either make spreadsheets like this that can do this stuff for you, or like we'll talk about next week, you can use Python to basically automate most of this so that you can just quickly generate your reports and your calibration curves and all that stuff. So sorry, density of benzene, anyone got it?
I found the molar mass and density for toluene.
Okay, go ahead.
The molar mass is 92.141.
Okay.
And the density is 0.87 grams per milliliter.
Okay.
And then the density is 0.8765 grams per cubic centimeters.
Okay, great. So I think from these data now, we'll be able to calculate our our molarities of each of these things, right? So let's go through and do it just for this first for the MTBE in standard solution 1. So where should we go with this? How are we gonna start? Using the Excel stuff here. So we know we're starting with 50 microliters of solution, right? And we want to eventually end up with moles per liter. So what should I multiply this number by to get it into liters first? We can just do that step. Or divide. So we can do multiply by what? It would be 1 divided by 1e6. There's 1,000,000 microliters per 1 liter, right? That should give us the right number. Let's just double check. So we do that, and that gives us this really small number of liters, right? And I think that makes sense. So let's just modify our equation then. So now we've got liters. So what's the next step that we want to get to figure out how many moles there are?
Multiply it by the density. You want to get it to grams?
Yep, so from that density, remember, so that density is in units of grams per cubic centimeter. So we'll multiply by the density real quick. And then what should we multiply that by in order to get it in grams per liter? And actually, we can do an extra pre-step here. So let's just multiply. These are all in grams per cubic centimeter, right? So let's multiply them over here to get those in grams per liter instead. So to multiply for this to get to grams, so could someone look up the conversion for cubic centimeters or milliliters to liters?
I think it's 1-to-1 centimeters cubed to milliliters.
Yeah, that's 1-to-1, but then milliliters to liters. So it should be just 1,000, right?
Yes.
Yes.
Yeah, that makes sense to me. So let's just copy that down. So this can be the number that we then use to actually multiply over here. So instead of multiplying by K2, we'll multiply by that number. And so now we have grams, right? So what's next?
Multiply by the molecular weight to get it.
So this, do we multiply by the molecular weight or divide it?
Divide it.
Yeah, so 1 divided by our molecular weight. So now we have moles. So what's the final step? We want to get it in moles per liter, right? So what do we need to do? We need to know the total solution volume, right? So how do we get that?
Do we just add all of the volumes?
Yeah, so we can do a couple things. We can either do within the formula here, we can add those things. So sum those, and I just realized I have a typo there, so I'll fix that in a second. We'll do that and then close that parenthesis. So that should be dividing by our total volume, but that volume is now in microliters, right? So we need to multiply that again by another correction factor, I think. So times 1e6. And so that actually ends up canceling the one we did here. So we can clean up our formula once we get this working here. So let's do that. And let me make sure that I add the correct number of values there. So 0.1168 approximately, right? And so you can go through and you can double check and make sure that we did the math correctly for that. But so that now that I notice that we have this extra thing in here, so why don't we just go through and modify this formula? We can take out that correction factor to go from microliters, and same with that one. And that should give us the same number. Yep, good. So now we've done the heavy lifting of making this formula work. We want to apply it to the other rows here. So we need to go through here and make sure that we lock the correct cells so that the formula can be applied correctly, right? So we want to be able to drag this down and across potentially, but let's first work on down. So we want the next one to be B3, so we don't want to lock this at all. We can lock, well, okay, so then L2, we want that to be the same one for all of them, right? So let's lock that cell. We want the molecular weight to also be correct. And then this one, we don't need to lock either. We want those to also go down to get the total sum there. So
Ben,
Yeah.
sorry to interrupt.
no, it's fine.
You mentioned that we should be looking at the lab manual on the, I can't find it on Gaucho Space.
Oh, that's a good point. I don't think that I put that in the lab folder this time on accident. One quick second. I will post it in Slack. And
Okay,
that
thank
way-
you.
Yep. And that way you guys can all download it real quick. That's my bad. GCMS, let's do lab manual, and I'll attach it. And this manual is kind of old, and so we're not following it exactly, but we are using the general procedure that it shows. GCMS, okay, that should be it. And I'll upload it. So that's in the GCMS channel, so you guys should be able to download that. Sorry about that, should have told me sooner.
I was just under the impression that maybe it was just because I couldn't download Open Chrome. Maybe it was there, but
Nope. That was my bad. Yeah, I forgot to include it in the file. I'll change that after this, but let's make sure that our thing works here. So that looks good, right? And again, I know that this is kind of overkill for this small of a data set, but imagine doing this for a whole bunch of different analytes and stuff like that. You want to set up these automation procedures so that you can quickly do this in the future. So we want to do the same thing now for toluene and benzene, right? So let's think about if we copy this formula over, let's see what needs to change to make sure that this is working. So C2 is correct, but we need this sum to still go from B2 to E2. So that's fine. And then of course, we don't want to use the density of MTBE anymore. We want this to be the density, we want this to be the density of toluene, and we want the molecular mass of toluene as well. So that should now work for toluene. Drag it down. That looks good to me. And then, so thinking about what we just did, we wanted to lock these things, right? So looking at the formula here, let's actually lock the columns, not the values. And that should make it so that when we drag that over, it should also work. So now if I drag that, it should give us the same number. Oh, I forgot to fix this again. Drag that down, that should be okay. And do that. Okay, so now if we drag this over, should have the correct sum. It does, but we need to modify this again to give our density and molecular mass of benzene this time. And there we go. So now what we have are concentrations in moles per liter of each of our analytes in the stock solution. So remember, for our actual samples that we run, we actually do a further dilution by taking 20 microliters of one of these solutions, then diluting it with 1 mil of the chlorohexadecane plus 50 microliters of the D8 toluene standard, right? So why don't we go through now and just calculate those final concentrations so that we can make an example calibration plot for one of these chemicals and just show that it's working. So the next steps, yeah, let me just write it out. We take 20 microliters of stock, dilute with 1 mil, I'm just abbreviating this, 1 mil CHD, add 50 microliters D8 tol standard. So one thing we maybe need to do is we need to go back and figure out our concentration of that D8 toluene standard. So hopefully now everybody's able to open the lab manual. So let's quickly calculate what our concentration of D8 toluene is in our initial stock of that internal standard solution. So everybody found that? It's 0.1 on page 4. So let's add some stuff to our table here. Let's do D8 toluene as well. So can someone look up the molecular weight? I'm going to assume that the density is the same as toluene. That might be wrong though. I think this is going to be like 98 or something, or 100. This one you can probably find on Wikipedia as well. And if not, you can look up on the NIST website. Let me see if I can find it too.
it says 100. Sorry, can you hear me?
Yep, I can hear you. Go ahead.
Okay, so it's 100.18,
Okay,
77. I'm sorry, 77.
100.77,
No. 100.1877.
1877. Gotcha.
Yes.
Okay. And then the density, I'm assuming, is the same as toluene since we're only changing the isotope. Is that right?
Let me look that up now.
Probably it's the same. We can just assume it for now. Okay, so let's now go through and think about the math to get from these stocks into our final concentrations, because we want all the concentrations, including the concentration of the D8 toluene.
It says the density is 0.943 grams per milliliter.
Really? It's that much different?
Yeah, unless I looked it up incorrectly, so maybe someone else can second that.
Yeah, good lesson. Verify. Someone want to look that
Yes.
up as well? D8 toluene?
Yes.
Because I'd assume it would be the same as toluene. I don't know why it'd be different, but whatever. So yeah, let's go through one of these examples for MTBE in solution 1 in our actual solution of the final sample that we're injecting. So we know we're taking 20 microliters, right? So let's just add a 20 there. And we want to get, so it's basically just a dilution calculation, right? We don't have to go through all of the different calculations that we did before, but we just want to take this value and then do like the M1 V1 equals M2 V2 thing. So our M1, right, is this one. And then so to solve that, here, let's just do this. So we want M1 V1 equals M2 V2. So if we solve this for our M2, which is what we're looking for, right? We want to do M1 V1 divided by V2. So let's go back here. And we want to divide this by a number that is going to be our total solution volume, right? So our total volume is going to be 20 microliters plus 1 milliliter plus 50 microliters. So why don't we just do all of that as microliters so that we don't have to do any other unit cancellations. So that would be 1,000 for that 1 mil plus 20 plus 50, right? Everybody agree with my math there? So that ends up with this really small concentration of the MTBE. And then if we want to make sure that we can extract this to make it work well, like actually this should, as it's written now, should be just fine to drag down and across. So down and across. So these now should be the concentrations of each of our analytes in our standard solution. And we should also make sure that we know the concentration in moles per liter now of our D8 toluene in this final stuff. So why don't we first do, what's our concentration of our D8 toluene stock standard solution? So that's 100 microliters of D8 tol diluted to 6.00 mils in 1 chlorohexadecane. So, okay, so where do we go with this? So our stock solution, I'm just going to do it underneath here. So 100 microliters times our density. Did anybody verify that density, by the way?
I found it, and it was something similar to what Lily found, the 0.943.
Okay, interesting. Let's go back and look up toluene again too, just to double check that, but I believe you. So 100 microliters times the density, which is now in grams per liter, but we're going to do the same thing we did up here, so we can ignore the conversion to microliters for now. So then divide by the molecular weight, D8 toluene, and then divided by our total solution volume, which nicely is just given in, we know that it's a total of 6 mils, so we can now divide that by, so 6 milliliters in microliters is 6,000, I believe. See if that makes sense. That number I think works, right? Someone can double check my math on that. But so this is our concentration of the stock standard solution. And we're taking 50 microliters of that and then diluting it to whatever the total volume is for these ones. So let's add that in here. So 50 microliters times, again, our M1, right? And then divided by our total volume, which is, let's just do it again, 1000 plus 50 plus 20. So that should be the molarity. It should be the same for, well, yeah, I guess it doesn't matter if we drag it down. It should be the exact same for all of them, right? Because we're not changing the volume that we're using of the D8 toluene standard. So everybody follow that so far. Understand why we're doing this procedure. I hope so. So now we have all the data that we need to actually start constructing our plots of our normalized area versus these concentrations, right? So let's go back to this table here, and we want to, let's do one for, let's do the MTBE one, just for an example. So let's grab all of these normalized areas, and I'm going to make another new sheet. So these ones we want to be on our y-axis. Whoops, we just want to paste the values. And then, so what do we put for the x-axis values for these different areas? Anyone got an idea? So let me also grab the labels for these. And I'll put them in here. Oh, okay, fine. We'll just put them in there first. We'll insert a column here. Sure. Okay. So we want concentration versus area, right? Caps lock. So where are we going to get these concentration numbers now? So for these different standards, we just calculated them, right? So for,
Yes.
for solution 1, we want this value here for the MTBE, right? So I'm just going to grab all 3 of these real quick. I know they're not labeled, but I'm just going to grab them. I'm going to put them over here for now. Whoops, we just want to paste the values again. So this is our concentration in moles per liter of our MTBE in our stock solution 1. So we want that there. And we're making the assumption here that whenever these vials were prepared, that the volumes that you transferred using like a micropipette or whatever were exact. We're not accounting for the area and the volume transferred there. We should technically, but for this lab, we're not going to. So we just want the same value then to be for all of these standard ones, right? And then same for standard 2. Put that there. Drag that down so it covers all the solution 2s, and then solution 3. All the same. So now, hopefully, this will give us some kind of calibration curve that we can then use to calculate things later. So let's grab a chart. I'm just going to do a scatter plot here. And so do these data make sense? Let's go through and actually do some prettying up of this data here. So what should this axis label be?
Concentration.
Yep. Concentration in units of moles per liter. And this one is what? Anybody got an idea of what to label this? Yeah, so this is normalized peak area. I think the technical way that we would want to do it is extracted ion count. And you could label this as normalized as well. So why don't we do that? Normalized extracted ion count. And so there's no units on this. It's just a count, right? This is a total number of ions that hit the detector. So then from here, I'm going to delete that title because that's a dumb title. So from this now, how do we get the equation that we need to calibrate so that we can measure the concentration of MTBE in gas? Anyone know what we should do?
Insert like a linear regression line, I think.
Yeah, let's try a linear trend line and see what that does. So you can see, yeah, so this kind of makes sense, right? So you can see that as we go up in concentration, we get a larger spread in our data. And so this is the reason that we did the triplicate style of data analysis and data collection, is because we end up with this curve here that kind of goes through the average of all these points and gives us a more accurate number then. So let's get the equation from that, and let's also display our R² value. Pretty good. So yeah, so this is basically the minimum thing that you need for a calibration curve for all of those different analytes now. So to summarize kind of the procedure we did, we normalized all of our data using our known concentration and area of our D8 toluene standard. This is why we included it. And we corrected all of those data by those normalization factors to end up with our normalized data. We calculated the actual concentrations in moles per liter for all of our analytes in our samples. And then we can plot that concentration versus that normalized area to get a curve for any given analyte. So now let's take a little bit of time and let's actually format this professionally. So like how you'd want to actually insert it into a report. So the default for Excel is nice for looking at on a computer and playing around with and stuff. But if you wanted to insert this as an actual figure, you need to go through and do a couple things here. So first of all, I don't like these gigantic numbers here for the axis. So I'm going really fast through this. So you guys should hopefully be able to watch the video back and look at what I'm doing. Or if you run into problems or questions about how to do some of this stuff, just let me know and we can go slower. But I want to format these. So the way to do that is to click over here, click on this number tab. And I just want to use scientific, I guess. And that's kind of fine. I'll do a little cleaning up so we don't have any numbers that have another decimal place there. So I'm going to take that one away. I don't like the two numbers for the exponent. So I'll just do that. That cleans it up a little bit. That looks kind of nice. These ones actually look fine down here. I might want to add some resolution to them. So for this axis options here, I want to go in steps of a little bit smaller than that. So I'm going to half that. I'm going to go 0.00025 instead. Whoa, that's too much. Sorry, didn't mean to go that far. 0.0025, that's too big. One more zero. So that gives us a little bit better resolution down there. That's fine. And these are kind of just personal styling choices. You could do it the same as it was. This is actually fine too. And then our minor ones are 1/5 of that. So why don't we show those? So tick marks, this is also something that should always be done for professional graphs. They should have tick marks along the outside. I also want to make the colors a little bit better. So for that axis, I want it to be black so that it's easily visible. Now I want to increase the thickness of it so you can see all those much better. Let's also increase our font sizes. So this one, something like that. So that's easily legible once you make a smaller figure with it. Change these as well. I'm just kind of making them arbitrary. You guys should make these standardized when you do them. And I also want to include, so let's fix the border on this one as well. So let's add solid line, make sure it's black, increase the resolution there. Also add some tick marks. We want to do outside, outside. We don't really need the extra resolution in there on the tick marks, so you could probably get away with just none for the minors there. That's fine. And then this one, we want to add a border around the entire frame here. So we'll also go here, solid line, black 1.25. So that looks better for the overall chart. I kind of want to make it more of a square because this is generally how things will be presented in an actual paper. And then a little bit more. So let's clean up this data as well. So these markers, we want them to be bigger. The filled circles is maybe fine. We'll use the circles. Let's increase the size of them so they're more easily seen. Instead of, let's do a solid border for these, and we can also just do blue for that. And then the fill, I'm going to try no fill, or we'll do a solid fill of also blue and just increase the transparency so that you can see all of the data a little bit better. So it's kind of noisy still. You can play around with these colors to make things look a little bit better, but in general, you want to do this with all your plots. You want to format them, make them look professional. this trend line as well. I want to give that a solid line. I don't want to do any dashes on it. Just want to do that. You can make the color whatever. Blue is kind of cool. And then if you wanted to extend this outside of the data, which actually for this we shouldn't, because all of our data should hopefully fall within this. But if you wanted to, there's this option with trend lines. If you go to this tab, you can forecast them. Let's try, I don't know. You have to pick, whoa, that's way too many. 0.05, also way too many. So this is different for all the data. You just have to experiment with like, so see, a really small number like that gives us just this little tail hanging off there, which is nice. And then we can do the same, the backwards direction. Up to you. And then the equation, which is actually the main thing that we're going to need. So this default format here is not super useful to us, but let's increase the font size because we are going to need it. So I want to go in here and I want to increase the resolution of these things because the slope of just 5E9 doesn't give us enough decimal points there. So this you should be able to change. Yeah, so number, we want to change the category to an actual number. Whoa. And so that made it so it just put the numbers in with the commas and stuff. So why don't we just change that to scientific? And then now we can increase the number of decimal places. I don't know, just give it a lot, something like that. So even though that changes all of these by the same amount, if you wanted to clean this up, you could take these numbers out and kind of just format them yourself and then overlay an image on this that has the correct formatting and stuff. But in general, we want to use these numbers with higher precision so that when we're doing our final calculations for concentrations, they're more accurate. And actually, I'm not liking how this goes below the axis there. So I'm going to take that backwards forecast off. 0. There, that looks nicer. Another thing, I'm just kind of flying off the cuff here, just doing things that I would do. So all these numbers are pretty small, and I would rather have them be kind of whole numbers. So instead of doing it in moles per liter, you could change this to like millimoles per liter, which would give us, 0.5, 1, 1.5. There's actually a way to do that within the axis formatting here. So we can, let's see, one of these things should allow us to, well, we can change this to number. And then of course it gives us that. So some more decimals, it's too many. 3, 4. So there should be a way to divide each of these essentially or multiply them by a certain factor that will change their scaling. So, okay, so display units, we can do thousands. No, that's not useful. Okay, so instead of that, what we could do instead is let's convert this into millimoles per liter. So this number times 1,000. Drag that down. And then when we select our data and go up to this chart design thing, we can just change the axis to be that instead. So select data, we'll edit it. And then the X values here, we'll just change it to this column instead. And now we have a whole bunch of nonsense with our axis, of course. So major, we want 0.5 instead. There we go. So that makes more sense. And then back to our numbers, we'll do 1 decimal point there. That's a little bit cleaner. And of course, change this to millimoles per liter. And so now we have a nice looking professional graph minus some formatting here. So one thing we could do is instead of saying Y, we could have count equals this number times concentration. And that makes it a little bit nicer there. And then I also don't really want that to be formatted in the center. I don't know why it's doing that. Whatever, it wants to center it. But anyway, so all these are little things that you can do to make your graphs look a little bit nicer. Another thing we can format this thing. So let's give it a background color of just white. Give it a border, some gray, and then extra fancy, let's just give it a shadow. Why not? So there. And then of course, this would need a title. So chart title, this is calibration curve for MTBE standard solutions. And then let's just put it right there. Increase the font size. I don't know, make it bold, who cares? Stuff like that. So there you go. So then this now, to actually save it in a way that you can embed this into a Word document, you can just copy and paste this, but some things can get messed up like that. So to avoid that, you can right click on the chart and you can save it as a picture. And this will allow you to save that. So let's go and just save it in our data file there, so it's in the right spot. Labs, GCMS, data for lecture. You can make a new folder and just call it figures or something like that. And then we'll call it MTBE calibration. So there. So now you can just really easily put that figure into your final report and go from there. So let's go back here and think about the next steps. So basically what you'll do is after you've done all of that for all of those different standards, you've made the calibration curves, you can even play around with plotting them on the same figures if you want, if they have similar retention times and areas so that they don't, make each other too big or too small. Then you'll go through and do the same kind of analysis for the gasoline samples, which remember are also doped with the same concentration of the D8 toluene. So you should be able to normalize the retention times and normalize the peak areas. Now, there's a little bit of trouble here. So this is why the data has kind of been provided for you guys already, but let's open up one of those example files that I sent. So there's a sample key here that tells you what each of these data files are. This is just how they get saved by the GCMS. But this one is an example gasoline sample. So if we open that up, you'll see that we now have a mess, right? We don't have nice 4 clean peaks corresponding to our 4 analytes. And so if you go through and kind of click on each of these, you'll see that they make up, like the stuff that makes them up is something else. And so what you'd have to do is go through each one of these peaks and find the ones that correspond to the correct retention time and the correct mass to charge signal. So all these ones I clicked so far, right, they don't correspond to anything that we're expecting. Well, let's see if I can get the peak of this one better. Let me just zoom in. So this one, yeah, this one looks like it doesn't maybe have the MTB in it. Yeah, so 71, that's nothing that we're looking for. 56. Come on, come on. 56, there's another 56 and a 71, so it's got a bunch of crap in it. So basically what you have to do is you have to go through and look at each of these things to see which ones correspond correctly to the actual analytes we're looking for. And at least we should know that we should at least be able to find the D8 toluene. And I think that's it. And if we look at the retention time there for those peaks, so let's look at the 98.1 peak, 98.1. So it doesn't tell me the retention time for it. Well, anyway, so it's about what? That's 2.9 or 2.8 minutes. So let's go quickly back and look at our standards to see if those kind of agree with what we had for our standards. Okay, so it's slightly less. And this can be for a number of reasons. It can be because of differences in the way that the sample is injected. There can be matrix effects. So all those different compounds in there can change how the compound interacts with the column itself. And so you'll have to go through and kind of normalize those things. And so actually, let's open up the gas standards. So let me actually find that and then open it real quick. I think I have this here. Not the raw data, we want the integration report, and let's look at the integration report gasoline. So this one has not been pivoted for you guys. Like you'll have to go through and kind of make your own summary report like we had for the standards. But all of these different ion peaks have been extracted kind of for you. And so for that sample, there were 3 different peaks in the chromatogram that corresponded to this dominant mass of 73. So they had different retention times here in different areas. So you'll have to base your analysis on these retention times once you normalize them to the D8 toluene. You'll have to decide if any of these really do correspond to MTBE or not based on that retention time from the standards. And so it's like for this one too, there's also 3 different peaks. You can see that there's these 2 out here that are after 6 minutes. And so if we go back again to our integration summary, that was for 91. You can see that from our standards, we expect the toluene to be eluting around 3-something minutes. And so those peaks that we see at, geez, so many things are open. These peaks around 6 minutes, probably not toluene. Even though they have the same ion mass, they're probably not toluene. So you would probably use this one when you're actually reporting the concentration of toluene. Same for 78, there's 2 peaks there. For 100, the D8 toluene, luckily we just have the 1, and this one's around 3.2 minutes. So these are the data that you're going to be using for your actual analysis. The data that I gave you guys in here are just for your benefit to kind of make some example plots, but the data from this are not the same ones that are in the integration report. The data from the report are just simulated so that you guys can get some good results. But these are just examples of what gas chromatograms look like for raw gasoline. So yeah, so does anybody have questions about the procedure for this and know what to do kind of?
Not really like questions, but I'm just still having like a bit of a hard time getting the Open Chrome to work.
Okay, are you on Mac or Windows?
I'm on Windows.
Windows 10?
Yeah.
Okay. So yeah, when you download the file for Open Chrome, let's see if I can find it on my computer here. Downloads, Open Chrome. So you get just a zip file, right? Let me see if I can just find that zip file. So this is what I downloaded right here, this Open Chrome lablicate.zip. You're able to get that file, right?
Yeah, I have that.
So in order to run it, you need to extract it. So you right click and then you can click extract all. And that'll make a folder that's uncompressed. And then within this folder, there's the openchrome.exe program. So if you double click that, that should run the program.
Okay.
Make sense?
Yeah. It's just like I tried that and I don't know, like I just got an error saying it wouldn't open.
Did you extract the file first, like you uncompressed?
Yeah.
Well, yeah, we can try to troubleshoot that together after if you want.
All right.
Yeah, does anyone have any other questions about kind of the analysis and the processing and stuff like that? Because I'll go into some of the report details that I'm looking for now, if not. Okay, so I'm going to go through this. And I realize that it is going to be quite a lot of work, given that, it's going to take a lot of time to go through that data and make sure you're processing it well and understanding what you're doing with it, and then generating the figures and things like that. And then also writing up all of the introduction material and the background and the results and the procedure and all that stuff. It's going to be a lot of work. So like I said at the beginning, I want to make sure that you guys aren't feeling too crunched for time on that. I want to give you enough time to do a good job on this. What I want us to do is we're basically going to write this as if we were writing an actual journal article. So I picked the advanced materials template just because they have a pretty nice one that you can download that's a Word file. So we'll be using that to kind of structure the format of your report. And yeah, so here's basically what I just said. It's a lot of work. There's not going to be a length limit on this. This is going to be pretty open-ended as far as what you guys want to include in the report. I mean, it obviously needs to be thorough and talk about all of the points that we basically went over today, including some of the background of how this method works. You also want to write it as if you were actually doing this experiment, like in the context of as a job, right? Like, so you have these gas samples, your goal is to get these concentrations of the different analytes. And so write it as if you were just doing that experiment, not as a lab for a class, but as an actual like a real experiment, right? Does that kind of make sense? Hopefully you guys have had some experience writing in that format. If not, we can talk more about it. And then as part of this preparation of the quote manuscript, all of the figures and chemical structures and drawings and stuff that you guys include should be good resolution and made for the actual report. So I don't want to see screenshots or cell phone pictures of like your screens especially. So all the graphs should be generated, if you can, as a vector format, so like an SVG or even a PDF or something like that. But PNGs you can get away with as long as they're high resolution enough. And then make sure that like you follow the template guidelines for the formatting and stuff like that. So they need labels, and the figures need to have labels, and you need tables and things like that. And you also should include references, kind of as many as you can. Here's a couple things, just some points. I can add more to this later, but things that you should kind of research and include when you're talking about the background and stuff for your report. You want to address like why we see the mass spectra we do. So like that point about the MTBE showing a peak at 73 versus 88. Talk about why that is. So a little bit of detail about EI and how it works with mass spec. And then a little bit of background about how the mass selection is actually working inside this detector. So why are we able to get this separation of the different ions? And then also talk about this procedure that we just did for normalization and why we do it and why the method that we use is appropriate for this use case. And then, yeah, so for the conclusion part, and obviously you don't have to start thinking about this right now. I don't even expect you to start writing the report until next week, basically, once we've done more of the analysis. But you want to talk about, yeah, the context of your data in the broader field of like, does what we found from our experiment agree with other reports for gasoline? So you'll have to do some research to look up other people's articles for doing something similar to this. Or you can even look up like EPA standards for concentrations of things in gasoline. If we see a deviation from those standards, like if there's some unexpected outlier, is it a real one? Like, does it make sense that our data could have that? And you have to validate that and make the argument based on the methods we use that it's real, or could there be some experimental error that would lead to that deviation, and then discuss that. And then it'd be nice also to include some discussion about how could we improve this experiment or change it to make it more accurate. Or are there other, other methods we could use for the normalization, for instance? Could we use different internal standards? Things like that. Just a little bit of discussion about, thinking about how we could potentially improve our results from this. And then, yeah, I'll publish this this PowerPoint as well on Slack so that you guys can click on the links and stuff that are in here. So if you can, try to get OpenChrome running so that you can make those CSV files from the chromatograms and the mass spectra. Hopefully you all at this point in your careers have downloaded Microsoft Excel, since it's free from UCSB. You can get away with using the free and open source versions like LibreOffice or OpenOffice and things like that. They should do the same thing. Google Sheets, I've had a lot of trouble doing some of these things in. Like, it has most of the functions, but it's just a kind of a headache to get things to work well. So I'd recommend just using Excel. And then you should include some chemical drawings of these analytes. So like the benzene and toluene, all those things. ChemSketch is free from ACD Labs. It can produce pretty good quality figures. ChemDoodle is technically not free, but it has a free trial. And I actually think that UCSB has a site license. So if you use your UCSB email address to get a key, you might be able to get this. I don't know that for sure, but you should try. And then for those of you that are on Mac and are having trouble with getting OpenChrome to work for whatever reason, or an old version of Windows, as one person does, you can consider these two programs. So Parallels or Crossover are really similar things. They basically just let you run a Windows environment natively on your Mac. And so you can download the Windows version of things. And actually, lots of scientists I know, actually pretty much everyone who has a Mac, has something like this where they can run Windows programs, because there's a lot of data analysis tools that are, for some reason, only built for Windows. So I'd highly recommend doing these. Parallels is something like $80. Crossover has a range of products ranging from like 30 to also $80. I've never used this one. I've looked at Parallels a few times, but I'm on Windows. So they both work. There's also a free way. If you want to take the time to dig into this, you can use this program called Virtualbox, which will allow you to make a virtual machine, it's called. And then within that, you can install Windows yourself. but you will need to get a copy of Windows somehow. You can buy it if you want, or there are some websites where you can obviously get it for free. Just be careful not to download a virus. And if you want some help with that, I can also assist. I've done this before myself. And okay, so the days are wrong. I'll go through and change this before I upload it. But for Monday now, so I'd like you guys to spend some time reviewing the recording from this and try to do as much of the analysis and plotting as you can. Whatever problems you run into, like I mentioned, make a note of it and then bring those questions to class on Monday, and we'll go into depth for how to do some of those things. And I'll also have more of a template for your reports that shows kind of like the structure and how you should arrange figures and tables and things like that. And then, so on Wednesday, again, this is going to be optional, I think, but a lot of you responded to that that Google form saying that you might be interested in learning how to do some of this with Python, which I think is very good and probably the most useful skill you'll get from your undergrad careers. So in order for us to get started with this and not spend forever, getting it installed for everybody's system, if you haven't done this already, I'd recommend doing it this way with Anaconda. This is like a really common way to install Python, especially for data analysis. So Anaconda is a free software package, and it basically lets you download Python and create virtual environments for it and install the packages that you need, because we're going to be using Jupyter, Pandas, SciPy a little bit, and Matplotlib to basically do all the stuff we just did in Excel, but automate it and make it faster. So do that, try to get it running. If you have any problems, again, I can help with that. I've got a couple slides after this that at least will let you test that. If you have zero experience with Python, I would really recommend maybe going online and just perusing some of the introductory Python materials. There's a lot of free ones out there. I think Codecademy still has free tools for doing introductory Python stuff, and those are really useful. I did those, I don't know, a couple years ago. And this will basically show you how to do really simple things in Python, like using print and adding numbers and all that stuff, which we'll be using to do the data analysis. So I don't want to spend a lot of time going over that really basic stuff in Python. Not basic in the sense that it's like beneath anybody. Obviously, like you need experience to do this stuff, and it just takes time getting used to it. But if we have to spend a lot of time showing how to like print things and add numbers and things, we won't get to the actual data analysis. So we're basically going to start from using Pandas to read in CSV data. And then there's some slides here that'll kind of guide you through how to set up an environment for doing this analysis. I'm not going to go through them now. You can download this and work through it on your own time. These are the packages that you'll install. We'll open up a Jupyter notebook, blah, 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 and then run some test code to make sure that everything is working correctly. So that is everything that I have for this week. I believe this class technically ends at what? Is it 8:50? Is that what it is on Gold?
Yeah.
Okay, I definitely don't want to keep you guys here that long unless you want, but I'm also happy to stick around for a little bit now if you guys want to start the data analysis or ask some questions or whatever else you guys want to talk about. So, any questions?
I was actually able to get Open Chrome to work.
Awesome, good.
Yeah.
Oh, we can maybe go back to our mass spectrum plotting here and figure out why that wasn't working. So,
One more second.
yeah,
The
go ahead.
lab manual, did you upload it to Gaucho Space or?
I sent it in Slack.
Oh, okay.
I will upload it to Gaucho Space after this.
All right. And you also sent the link for the Open Chrome through Slack?
Yes, that's also in the GCMS channel.
Okay, thank you.
I'll do the vast majority of communication in Slack. I hate emailing. Okay, so yeah, feel free to ask more questions. I'm gonna try to troubleshoot this and figure out why it's not correctly labeling the data. So, okay, let's try doing this. That's probably just gonna give it a weird, yeah, that's not gonna work. Okay, so what is different about my key here? So let's look at this one, select the data. Okay, let's try that. Chart design, select data. Ah, okay. So let's just remove that, add a series. The values we want to be that. And this, okay, here we go. Oh, up. We want this to be the labels. Tell me that worked. Hey, that's better. So now, yeah, I don't know if anybody's left or not. So now we actually have our axis is the masses and our y-axis is the counts. So from here, to make it look a little prettier, we'd want to edit the format of our data and stuff like that. Let's see. Click on this. We want to make these. Can give them a solid fill of black and then border also black, and then we can just increase the thickness there, and that should give us a more clean looking mass spectrum. So then if we want to label the points, so I guess you can select individual ones, and let's add a data label. So that gives us count. We actually want just the mass. So we want the series name, not the value. Whoops. No, not series name. So sorry, you guys are so quiet. Does anybody have any questions actually about the other data analysis and stuff?
How do you import the files into Open Chrome? Do you just open with? Is that?
Yeah. If you, so once you open the, let's see, when you open the file, it should open up this Data Explorer tab here. And then if you navigate to, God, where are my files now? If you navigate to the folder where you've downloaded the actual files. So in here, you can see we have our raw data, or these .d files. And then if you just double click on the data.ms, it'll automatically load it like that. Yeah, these files contain a bunch of the information. So all of the chromatography stuff, as well as the counts for each scan. I was trying to find a way to open these some other way, but basically it's a proprietary software format. And so if you open it in some other thing, let me see if I can find it here. Let's see, so let's open this. Open it up as a text file. It's just basically a bunch of garbage. So I haven't found a way to read these with anything besides this Open Chrome software, which is unfortunate. Yeah, so it's got some, yeah, it's hex encoded, and it's just a bunch of garbage. So you need some software to decode it. See, there's a couple strings. So there's a date. So this was apparently collected in 2018. But anyways, yeah, so Open Chrome is the way to go for now until we can find a better way. But yep. Any other questions? Data labels are garbage.
Thanks, man.
Yep. Yeah, if no one has any other questions, you guys can leave, but I'll stick around for a while if you want to work on the data.
Thank you.
All right, thanks.
Yep.
Will you be able to post this recording on Slack or Gaucho Space?
Yep, I will. Once we're done here, actually, I'll just stop the recording now, and we will. Yeah, I'll upload it on Slack for sure.